The last topic I want to talk about regarding work and energy is power. And power is just defined as the rate at which we do work on a system, at which some force does work on a system. And the simplest illustration I can think of power is, and why power is a useful concept, is to think about weightlifting. Okay, I think the world record for a deadlift is something like 600 kilograms. That is, the world's greatest deadlifter can pick 600 kilograms up off the floor and lift it about a meter into the air as they stand up. Okay, so how much work does it take to deadlift 600 kilograms? Well, the work required equals the force required times the displacement. And the force required to lift a certain amount of weight is just the amount of force you need to overcome the gravitational force, which is just m times g, so mg delta x. So the amount of work required to deadlift 600 kilograms is going to be 600 kilograms times, let's just approximate g as 10 meters per second squared, times about a meter. So 600 times 10, that's about 6,000 joules of work. Okay, so that's how much work it takes to deadlift 600 kilograms. And I certainly can't do that, but what I could do is take all the weights off the bar and lift them one at a time and set them on a table that's a meter above the ground. And if I do that, the amount of work that it takes to lift all that weight a meter off the table is exactly the same. I can still do that 6,000 joules of work. So clearly work doesn't really identify the difference between a normal person and a championship weightlifter. So the key difference is in power. If this weightlifter takes 1 second to lift this weight by 1 meter, well then their power is the work that they did divided by the time that it takes, delta t. So this would be 6,000 joules divided by, 6,000 joules divided by 1 second, which is 6,000 joules per second, and the units of power are watts. This is 6,000 watts of power. Now it's a little confusing because we use W for watts, we also use W to mean work, but you need to be able to tell by context whether we're talking about watts or work. This is power, 6,000 watts, or 6,000 joules per second. Okay, if I say this is a bunch of 20 kilogram masses that make up this 600 total kilograms, that would mean that there are 30 of these 20 kilogram masses, and therefore I would have to lift these 30 times to do this same amount of work here. So let's say each lift takes 1 second. So for me, the power that I deliver would be the same amount of total work divided by my delta t, which would be 6,000 joules over 30 seconds. 6,000 joules over 30 seconds is 200 watts. So you can see there's, even though the work that we do is the same, there's a huge difference in the amount of power we deliver. Okay, so power is really useful as a way to characterize how good some person or some machine or some animal is at doing work. Over some time interval, we can define the average power as the work divided by that time interval. But we can also define an instantaneous power. If the work is being delivered continuously, then we can't just take the work and divide it by the time interval. We have to take a derivative of work with respect to time to find the instantaneous power. And this instantaneous power can be written as the dot product of the force and velocity vectors. Okay, that seems a little weird. Let's take a minute and see why that's true. So let's say we have some object and we apply a force F to that object, and it moves through some displacement vector, some little displacement vector like this, and we'll call this little displacement vector dr. Okay, it's just a little small displacement, really an infinitesimal displacement dr. Well, if we want to find the work that we do on this object during that displacement, we would take the dot product of this force F with dr. Since this is a little tiny displacement, we're going to say this is a little tiny amount of work, a little infinitesimal amount of work we do over this little infinitesimal distance. Well, to go from this work to power, we just have to divide both sides of this by dt, the amount of time it takes to do this work. So this gives us, well, dw dt is just the power, p, equals F dotted with dr dt. Well, dr dt, that's the change in the position of this object with respect to time, which is just the velocity. So we see right here that this power just equals the force dotted with the velocity. So we can always find the power that some force is delivering to an object by taking the dot product of the force vector and the velocity vector of that object. So here's an example of a problem involving power. A car with a mass of 1,000 kilograms accelerates from 0 to 20 meters per second in 4 seconds. A. Ignoring drag, what is the average power delivered by the car's engine during the acceleration? B. The drag force at 20 meters per second is 100 newtons. What power is required to maintain the car's speed at 20 meters per second? And C. What power would be required to maintain the car's velocity at 40 meters per second? Okay, so let's start out. For part A, well, we want to find the power delivered to the car, the average power delivered by the car's engine during the acceleration. The average power equals the work done by the car's engine divided by the time interval delta t. Now, there's a few ways we could find the work done. We could try to find the force and then integrate the force over the displacement, and we could find out how far the car goes during this first 4 seconds. But there's an easier way to do this. We can just use the work energy theorem. Work energy theorem says that this equals delta K plus delta U plus delta E thermal all over delta T. Okay, so we're going to say that this is on a flat surface. If it's not on a flat surface, if the car's going uphill, then we would have to worry about delta U. But we'll just say it's on a flat surface, so we can just say delta U is 0. That is, there's no change in potential energy of the car. And right now we're ignoring the drag force. So we're ignoring dissipative forces. We'll say that delta E thermal equals 0. This isn't really realistic, but it's good enough for now. So all we have to worry about is delta K. Well, that tells us that P average, the average power delivered by the engine of the car, equals delta K, which is K final minus K initial over delta T. Well, K initial, the initial speed of the car is 0, so K initial is 0. This just equals 1/2 m v final squared over delta T. So the average power equals 1/2 times 1,000 kilograms times 20 meters per second squared. Divide all of this by delta T, which is 4 seconds. I plug all this into my calculator, and I get that this average power equals 50,000. And my units are kilogram meters per second squared per second. Well, this is just a joule up here per second, which is a watt. That's the units of power, joules per seconds or watts. So this average power is 50,000 watts. That's how much power the engine has to deliver to the car to accelerate it from 0 to 20 meters per second in 4 seconds. Okay, part B. The drag force at 20 meters per second is 100 newtons. What power is required to maintain the car's speed at 20 meters per second? So Let's draw a free body diagram for this car. Well, it's going to have mg, and it's going to have a normal force. There's going to be a force pushing the car forward. Well, we actually know that the force that pushes the car forward is the static friction force. That static friction force comes from the fact that the engine is spinning the wheels. So the static friction force is ultimately being provided by the engine. So I'm just going to call this a force F that's pushing the car forward. And then we also have a drag force, D, that pushes the car back. And in equilibrium, F has to equal D. We know this car is in equilibrium because the velocity of the car is constant. It's maintaining a constant speed of 20 meters per second, which means that the acceleration of the car equals 0. So we can say that this force F minus the force D equals 0. That is, F net equals ma. I can ignore n and mg. I know those just cancel out. So I get that, actually this is F plus D equals 0. So I get F equals minus D, which means that the magnitude of F is the same as the magnitude of D, which equals 100 newtons. So this car is driving at 100 newtons. This force vector F then, let's say this is the y direction, and this is the x direction. This force vector F equals 100 newtons I hat. And our velocity vector V is going to equal 20 meters per second I hat. So I can use my power, my dot product formula to find the power. That is, I know that the power delivered by the engine of the car equals the dot product of the force with the velocity, which is just going to equal 100 newtons times 20 meters per second. Multiply those out, I get 20,000 watts. So just to maintain the car's speed at 20 meters per second takes 20,000 watts from the engine if this drag force is 100 newtons. Okay, so let's go on to part C. What power would be required to maintain the car's velocity at 40 meters per second? Well, the power would still be the force dotted with the velocity. But now if we drive twice as fast, the force required to keep the car going at the same speed has to increase. This drag force D is proportional to the speed squared. So this means that D has to increase. If the speed doubles, D has to increase by a factor of 4. So that means D here equals 4 times 100 newtons, which is 400 newtons. Since drag force scales like velocity squared, if I double the velocity, I have to increase the drag force by a factor of 4. So that means my force F also increases to 400 newtons. So here F now equals 400 newtons I hat, and V now equals 40 meters per second I hat. So I take the dot product of these to find the power. I get the power equals F dot V, and I end up getting 40 times 400 is 160,000 watts. So my power increases by a huge amount. It increases from 20,000 watts to 160,000 watts. It increases by a factor of 8. And that's because I double the velocity and I quadruple the force, since this force is proportional to the velocity squared. Okay, so that's a nice simple example of a problem you can do involving power. You have a few problems on your homework about power. And mainly power is useful as a way to characterize how good like I said, how good a machine, a person, or an animal is at doing work. How fast can they do this work?